Let us consider a sinusoidal wave equation. P equal to Vm cosine omega t plus phi. Here Vm is the amplitude and omega t plus phi is the argument. Phi is the phasor. Now we already know that for resistor the relation between voltage and current is like this, and for inductor there is a voltage and and current relation is like this, and for capacitor current and voltage is like so. These are the relationship between voltage and current for resistor, for inductor, and for capacitor. And if so, for resistor, that is voltage is proportional to the current, and for inductor, voltage is like L, the derivative of current times L, and for capacitor, the capacitor's current is the time derivative of voltage times capacitance of the capacitor. So for every case that doesn't interrupt the frequency. So for example, for resistor, if we operate a resistive circuit, either a voltage source or a current source, the response of this circuit will have the same frequency of the source. Similarly, if we operate an inductive or capacitive circuit, inductor or capacitor from a AC source, the response of the circuit component will have the same frequency for the source as the source. So now, as the frequency remain constant, only the change will happen to the magnitude and to the phase angle. So therefore, we don't need to consider three parameters for analyzing AC circuit. Rather, we need to consider only two parameters, like the amplitude and the phase angle. So it would be sufficient if we can find what will the amplitude, magnitude, and the phase angle of the response, then we can have the full information of the circuit response. So let us show you how we can get or transform my time domain expression, that expression which is as a function of time, to only in the frequency domain, like the expression is independent to the time, or skipping the time variable from the time varying component. So now we will express the sinusoidal wave equation from time domain. Given in time domain, we can write it like V equal to Pm e to the power j omega t plus phi using with the help of Euler's formula. But the Euler's formula basically tells us the relationship of Euler's formula gives us this expression like this: e to the power j theta equal to cosine theta plus j sin theta. So now if we want to write e to the power j omega t plus theta, so this will be cosine omega t plus theta plus j sin omega t plus theta. So if you write the expression in terms of e to the power j omega t plus theta, then basically it includes both cosine and sine. So if I want to get only the cosine, so we should take the real part of this expression, omega t plus theta. The real part of this expression will be cosine theta, cosine function, and the imaginary part of the Euler's expression will be the sine theta. So therefore my expression here is complete, includes both sine and cosine. If I take the real part of this, then it will include only the cosine function or cosine wave. So now I am taking V real this with the help of Euler's theorem. Now let me take this, expand this e to the power j omega t and e to the power j phi, and then we write it e v m e to the power j phi times e to the power j omega t. So now with the help of Euler's theorem we can separate the time function or time part and from the amplitude and phase part. So it got amplitude and phase, and this is the time part of this or time function. So from here we assume that this part is Vs to the power j omega t. So where Vs is equal to Vm e to the power j phi. So this is Vs is the frequency domain voltage, a frequency domain parameter, frequency domain quantity. So here we can write it in frequency domain. So the time domain V that we have started with can be written like Vs, where Vs will include the amplitude and the phasor, So finally we can write this Vm e to the power j phi can be written in the polar form j phi, or in rectangular form we can write it like the x function plus jy function. So you can write Vm the real part and the imaginary part. So Vm x or real part plus j of Vm I, the imaginary part. So this will be real part and imaginary part. So this is how we can convert a sinusoidal wave equation in time domain to frequency domain. Now let me give some example. So if we have, so let me show you this. Some examples here. So we started with Euler's identity, and then here we see the real part of this Euler's expression is the cosine, and the imaginary part is sine. Now, if we have an expression like Vt, Vm cosine omega t, now we can find the frequency domain part like this. Sometimes some textbook they use frequency domain they use the symbol like this to represent the frequency domain e to the power j theta, like sign on the top of V, and some textbook they use uppercase V for frequency domain. So in next exam for the subsequent chapter we will be using uppercase V for frequency domain. So we are going to drop the suffix s, but however the suffix s or the uppercase V both mean the same, so they are in frequency domain. So if you see a symbol like this or ps suffix s with V or uppercase V, they all represent the frequency domain parameter. Now, how we can convert time domain to frequency domain? Like if you have a time domain expression Vt equal to Vm cosine omega t, so you can write it as Vm angle is 0 degrees, or in Cartesian you can write Vm plus j0. Similarly, if we have a Vm sine omega t, so we need to convert it to cosine first, so we write it cosine omega t minus 90. So I like to explain it again. So you see here, so if you have sine omega t, and this side is cosine omega t. So if you have sine omega t is the function somewhere here, so your Vm is here. Now if I wanted to represent or express this with respect to cosine, then you have to write it like cosine here, and so this is your reference line. From this reference line you have to go 90 degrees from this way, so this is negative theta. So if I move this direction, my theta will be negative, so it is negative 90 degrees. So theta equal to negative 90 degrees. So we write cosine omega t minus 90 for Vm. So I replace sine omega t to cosine, then this becomes Vm, the angle is 90 degrees. So Vm is in polar form, so in rectangular form it will be 0 minus jVm. So if you have 90 degrees, 90 degree meaning is j. I also show you on the Euler's theorem. So you see, if you have j 90 degrees or pi over 2 will be cosine pi over 2 plus j sine pi over 2. Now if you put value for pi over 2, cosine pi over 2 is 0 and sine pi over 2 is 1, so it's equal to j. So e to the power j pi over 2 meaning is j. So that means e to the power pi over 2 is in the polar form. E to the power j pi over 2 in the polar form will be 1 angle 90 degrees. 1 angle 90 degrees. So 1 angle 90 degrees is the polar form, and its equivalent rectangular form will be j. So similarly, if you have a negative 90 degrees, it's equivalent to negative j. Now if you have a expression like 10 cosine omega t plus 30, you can write it like 10 30 degrees in frequency domain, or the respective Cartesian form is this. You can use calculators for getting the Cartesian form or equivalent for this polar. Then IT, let's say we have given a IT in time domain 22 cosine omega t plus 45. So we convert sine to cosine first by subtracting 90 degrees from the expression. So now it becomes cosine omega t minus 45. So this value is now, the magnitude is 20 root 2 and angle is minus 45 degrees. So in polar form, and in rectangular form it will be 20 minus j20. So however, in some case we might give you time domain expression for voltage or current. You need to find frequency domain before solving the circuit. And if we give something in terms of sine theta, or in terms of, or you have to convert it cosine first and then solve it. And if we give you sometimes in some values in terms of cosine, just you can use the amplitude and the phasor for representing the polar form, or also you can find the respective rectangular form for them. Now I'll discuss about steady-state AC analysis. So a steady-state AC response basically will be starting with AC source. We have voltage source and current source. It could be independent and dependent. So independent voltage source, independent current source, dependent voltage source and dependent current source. So voltage source expression may be given in frequency domain or in time domain. So if the expressions are given in frequency or time domain, frequency domain or time domain, you need to convert them in frequency domain. And sometimes we might need to know the RMS value. I'll discuss the RMS value later. So let me give an example. So it might give you a current expression like this: 5 cosine omega t minus pi over 4 ampere. So you have to find the equivalent current in frequency domain. That will be I equal to 5, angle is pi over 4 ampere. So this is my respective frequency domain expression. We also discuss about the circuit elements and the characteristics, voltage and current characteristics for resistor, capacitor and inductor. We also already show you what is the relation of voltage and current in terms of time domain. Like we already know that for time domain, voltage is V equal to IR for resistor, and for capacitor IC equal to dV over dt, and for inductor VL equal to C dV over dt, and VL equal to L di over dt. So you know the relation in the time domain. Now we need to find the relation in frequency domain. So we have to know the Ohm's law in frequency domain, as well as the voltage and current relation for inductor in frequency domain, and voltage and current relation for capacitor in frequency domain. So let me find Ohm's law first in frequency domain. So Ohm's law in frequency domain, you see, for resistor V equal to I times R. So if you assume that your I equal to I m cosine omega t plus theta, then V will be I m cosine V will be I m cosine omega t plus theta times R, or you can write I m times R cosine omega t plus phi. So now if I convert the frequency domain expression for I, it will be I m times theta, and if I convert the frequency domain voltage expression, then it will be I m times R cosine angle theta. So you see Vs is basically I m theta times R. So just Vs equal to Is times R. So for time domain case, it was V equal to I times R. Here for frequency domain, it also B equal to I times R. If we drop S, we'll get I times R. So for resistive circuit, for resistors, Ohm's law is quite similar. B equal to I times R, and also B equal to I times R here. So now for inductor, if we think inductor or inductive circuit, so let's assume your I t equal to IL cosine omega t. So in frequency domain, it will be I equal to IL 0 degrees. Now VL equal to L di over dt. So if I take put the IL cosine omega t and take the derivative of this, you will get L omega IL sine omega t. And sine we can convert to cosine. There is a negative here, so it will be cosine omega t plus 90. So now if I write in this VL in frequency domain, then it will be uppercase VL and omega L prime, and angle is 90 degrees. So I convert this to frequency domain. So here you see for J 90 is equal to J. The angle 90 is equal to J according to the Euler's theorem. So you get J omega L IL. And J omega L, we can use a new variable for this, new parameter, that is ZL times L. So for the Ohm's law for inductive or inductor is like VL equal to ZL IL, and where ZL is J omega L, and sometimes this omega times L we can use XL, and this XL is called inductive reactance. Inductive reactance, and this Z is we use impedance. The name of this Z variable is called impedance. So ZL basically inductive impedance, and X, the variable, is called reactance. This is called inductive reactance, and ZL is equal to J times XL, and XL equal to omega times L. Omega is the frequency and L is the inductance of the inductor. Similarly, capacitor and capacitive reactance. So let's assume Vt equal to Vc cosine omega t. I convert to frequency domain, so it becomes V equal to, the amplitude is Vc and the angle is 0. Now Ic is C dV over dt. So if I take derivative of this, it will be C omega Vc this. So you can write cosine omega t plus 90. So Ic equal to J omega C Vc 90. And here 90 degrees we again replaced by Cartesian component. Cartesian, that will be J omega C Vc. So Vc be equal to Ic over J omega C. So here 1 over J omega C is Zc. So we got the Ohm's law is V equal to Zc Ic. So you see here for resistor we got V equal to IR. For inductor we got V equal to ZL IL, and for capacitor we got V equal to ZC IC, and where ZC equal to 1 over J omega C, and 1 over J can be written as negative J. As you know, 1 over J square, 1 over J, so you can write it like, if I write it like J square minus J square over J, because J square equal to minus 1, so you can write it like minus 1 over J, right, and minus 1 is j square over j. So you can cancel this square, we'll get minus j. So 1 over j is basically minus j, negative j, 1 over omega c, or 1 over omega c can be written as xc. So xc is 1 over omega c, and negative j of xc is zc. So now in frequency domain, we got Ohm's law for frequency domain. For resistor, we got V equal to I R. For inductor, we got V equal to I ZL. For capacitor, we got V equal to I ZC. So here we use ZL and ZC. So let me use ZR for resistor. So I use just a common term, that is the impedance. So this Z is for impedance. So this is resistive impedance, inductive impedance, and capacitive impedance. So you can use R or ZR, they are the same. So R is resistance, and if you want to make a common parameter impedance for each component, then you can write R equal to resistive impedance, inductive impedance, capacitive impedance, or you can write R and X. So Z, for example, if you have a circuit with R and L, so R and L, then the Z of this circuit will be R plus ZL. So R and ZL is J omega L, and omega is the frequency of the source signal. So the inductive reactance, or sometimes we can write it R plus J of XL. So for the inductive reactance is depending on the frequency, it depends on the frequency. So if you go for higher frequency, the inductive reactance will be higher. Similarly, if you have a circuit with both resistor, inductor, and capacitor, so the total impedance of this circuit will be R. For resistor, for inductor it will be JXL, and for capacitor it will be JXC. So it is negative. So that is R, or we can write it like R plus ZL plus ZC, JXL minus JXC. So you can write R plus XL equal to times omega times L, and this is J omega times C. So you can find the reactance like this. Now if you want to find the value in polar form, so what will be the value? Then for polar form you can write R. So I rearrange this like XL minus XC. Then in polar form it will be Z equal to R square XL minus XC squared, the square root, and the angle will be tan inverse XL minus XC over R. So this is how we can find the total impedance of a RLC circuit or RLC component. So if you have R, inductor, and C, then you can find the total impedance by using this formula. So this is the rectangular form, and this is how to find the polar equivalent of this. Now we also need to know how to find the Phasor diagram. So sometimes it is very important to know the phase relationship between voltage and current. So as you see here, expression like V theta 1 and the current expression like I theta 2, and as you know, we do have a magnitude and an angle, and sometimes we need to know which quantity leads and which one lags. So to find the leading or lagging component, we need to know their phasor relationship or phasor diagram. So how we can find the phasor diagram? So to find the phasor diagram, just we see how to draw the phasor diagram. So let's give an example like V equal to 530 degrees, it's this volt, and current I equal to 2 angle 45 degree like this. So to find the phasor diagram, we take a reference line like this. So this is my reference line, and then voltage got magnitude 5 and angle 30. So let's assume make a 30 degrees with this reference line, and magnitude is 5. So this is my voltage got 5 and angle is 30 degrees here. Now we solve for we plot current here on this expression. So current value is 2 and angle 45 degree. So current is 2. So now if you look at this is my reference line. So if you look at this, you'll see your current makes higher angles here, and voltage is falling behind the current. So that means you can say current I leading. And this diagram is called phasor diagram. So phasor diagram is the diagram showing the relationship between voltage and current. So phasor diagram shows the phasor relationship between circuit voltage and current. So we might ask you to draw the phasor diagram of a component of the circuit. So to draw the phasor diagrams, basically you need to show the voltage phasor and current phasor. And also we might ask you to find the leading or lagging circuit or lagging component, if the circuit is leading or lagging. So if I is has higher angle than voltage, then I is called leading, and if I got lower angle than voltage, that I is called I is lagging. So leading means current leads the voltage, and lagging means current lags the voltage or voltage leads. So now if you see for a resistive circuit, let me start with a resistive circuit here. So let's say in this resistive circuit we are given 50 cosine 370 plus 45 degrees, and the resistance value is 5 ohms, and we have to find the current in this circuit. So here the voltage is given in time domain, so we can directly use time domain here. Voltage equal to IR, I equal to V over R, So the expression will be 510 cosine this. So time domain is okay for resistive circuit. But in frequency domain, we also can solve this circuit in frequency domain. For in frequency domain, you have to convert this expression into frequency domain. So the frequency domain voltage will be 50 and angle is 45 degree. 50 45 degrees and resistance is 5. So you can write V equal to IR. In frequency domain, you can use uppercase V, uppercase I for this cap on the top. So V times IR, I equal to V over R. 50 45 degree, 5, so it gets 10 45 degree. So this is in polar form. If you want to use the rectangular form, that's okay. So this is rectangular form. Now if I want to find the phasor diagram here, so if you look at the voltage phasor got 45 degrees and current phasor also got 45 degrees. So if I take a reference angle here and I make voltage with 45 degree and current in 45 degree, so you see voltage and current in the same phase, in phase, so they are called in phase. So voltage and current in phase. So and so the Ohm's law in frequency domain, as you know, is equal to V over I equal to 50 degrees. So V over I 55. If you know the voltage and current, you can find the impedance of the circuit. So impedance is equal to voltage over current, and that is 5. That is given here, and this 5 is equal to R. So R, if you wanted to convert R into Z, so R will be 5 angle 0 degree. So then this R goes to in frequency domain. So now look at a capacitor circuit, capacitive circuit here. So we have 50 cosine, the same voltage we apply to this circuit too, and this is the value for capacitance, C equal to this farads. So now in time domain, C equal to dV over dt, and if we convert this expression to frequency domain, so we already know that I will be J omega C times V, or you can write it like, as I explained before, that Z equal to V over I 1 over J omega C. So J omega C minus XC. So XC equal to this. So the in frequency domain, it will be V equal to I Z C. So here I will be V over ZC, and V is given, V is 50 angle 45, and ZC we can find ZC equal to negative J XC, or you can write negative J omega times C. So omega is given 377 and C is 0.000265. So we already solved it here. It becomes 0.1. So that is 10, J10. So Z equal to J10. So you can find ZC equal to negative J10 ohms. The unit is ohms. So now you can find the current. And if you find the current here, you will get the current angle is 135 degrees. So you see current angle is 135, voltage angle is 45. So if you plot them with respect to this reference, you see voltage makes 45 degrees and current makes 135. So current leads. So in a capacitor circuit, current always leads the voltage. And if you see the difference between voltage and current is 90 degrees. So capacitive circuit or capacitor, purely capacitive circuit, makes 90 degree current lead. So voltage is behind of current by 90 degrees, and it is obvious that the derivative of cosine is sine, and there is 90-degree phase difference between a sine wave and a cosine wave. Now if I look at inductive circuit here, for inductive circuit I took current expression. So you see here current amperes, so this is a current expression, 10 cosine this, and inductance is this, and we have to find the voltage here. So to find this voltage, how we can convert this circuit to frequency domain. So let me convert this circuit to frequency domain. So the given time domain equation is 10 cosine 377t plus 45 degrees, and the unit is amperes, so it is a current source, and you have to find the voltage here. L is given like 0.001326 and this. So now this is a time domain expression, and I wanted to find the frequency domain expression for this frequency domain circuit. So in frequency domain, this current will be 10 and angle is 45 degree ampere, and for frequency domain the impedance will be ZL, and this will be V, and this is ZL, and ZL is equal to J of omega times L. So J and omega equal to 377, and L is equal to 0.001326. So if I find this will be 0.05, J equal to 0.5 ohms. So now if you want to find this voltage equal to V equal to I times Z. So this is the Ohm's law in frequency domain. So voltage equal to I times Z, and I is 1045 degrees, and Z equal to J 5.5, or you can write Z 45 degrees times 0.5, and J is equivalent to 90 degrees. So this, so that will be 5 times 90 40 135 degrees. So this is volt. Now if you wanted to draw the Phasor diagram is the relation between voltage and current. So you see the voltage here is this and current is this. So the voltage is 135, current is 10 this. So now if you want to draw the voltage diagram, let me think this is my reference line, and I have to go 45 degrees, and this is my current I at 45 degrees. Then 135 degrees is the voltage. So 5, and angle is 135 degrees. And again the difference phase angle difference between voltage and current is 90 degree, and here you see current lags. Current is lagging. So inductive circuit or inductor always produce lagging current, and capacitor produce leading current, and resistor produce in phase current. So for resistor, the current will be in phase with voltage. For inductor, current will be 90-degree lagging the voltage, and for capacitor, current will be 90-degree leading the voltage. So we have to learn, in addition to the Ohm's law that we have already discussed, we need to learn about Kirchhoff's voltage law and Kirchhoff's current law in frequency domain. So Kirchhoff's voltage law is basically the sum of the voltage. So in this case, the sum of the frequency domain voltage is equal to 0 in a given closed path or given loop. Sum of the all voltage rise or voltage drop in a closed path will be 0. So the same idea for DC circuits, but here we can use for AC circuit, but voltage in frequency domain. Similarly, the Kirchhoff's current law, the idea is same as we learned in for DC circuits. For AC circuits, the idea is same, but here we use in frequency domain. And also combination of impedances, like here the combination rules for impedance is same as the combination for resistance we discussed for the DC circuits, but we combine impedances, not the resistance only. So we need to find the series. If the impedances are connected in series, we can add them together. If the impedances are connected in parallel, then we can use the parallel combination law. Like for example, if you have few impedances in series, let me give an example here. Yeah, let us consider RLC series circuit. So here you see we have an resistor, inductor, and a capacitor, and this is the voltage, AC voltage excitation. So now for this circuit you have to find the current, and also we have to find the impedance diagram and phasor diagram. So let me start with, so at first we have to do convert the circuit to in the frequency domain. So I convert this voltage source, so this voltage source, and I'll convert this resistance, this inductance and capacitance in frequency domain. So let's start with this resistance. So this is 5. So if you want, you can write it 0 degree or simply 5, that's okay. Yeah, there is no need to write 0 degrees, but that's okay too. 0. Then I convert this in frequency domain, and then I convert L into frequency domain. So L will be Z2. The impedance of this is omega L. So this one got J5 ohms. So now you see this is ohms, this also in ohms, and then the impedance of this is Z3 1 over J omega C, and this is negative J, and omega is 1000 and C is this, you got negative 10. And this voltage I convert to frequency domain, that is 50, and angle is 45 degrees. Now they are connected in series, as there is only one path to conduct the current. So you add them together, Z1 plus Z2 plus Z3. So if I add them, this is 5, this is J5, and this is negative J10, negative J10. Then the equivalent total will be 5 and J negative 5. The real part is 5 and imaginary part is 5 and negative 10. So this is negative 5. And this will be the polar form. You don't need to find this polar form because calculator can operate in mixed mode. If some values are in polar and some of them are in rectangular, your calculator can work on them at the same time. So it is not necessary that all values should be in in polar form or in rectangular form, you can use mixed mode, like some values in rectangular, some values in phasor. So here we got V equal to 50/45 and Z equal to 5√245. So 5√2, if I divide them, got 5√2 times 90, as angle is 90, or J 5√2 ampere. Now the impedance diagram, basically impedance diagram showing the impedances in this circuit. Here see the R has 5, angle is 0 degree, so I write R in this way. Then XL is J5, so that's equivalent to 5 angle 90 degrees, and this will be equivalent to 10 angle negative 90 degrees. So I make XL with positive 90 degrees and XC makes negative 90 degrees with R. Now we have three vectors, R in this way, XL is this way, and XC is this way. We can add them and to find the resultant. Resultant is here Z. Our resultant Z you already found, that 5√2 angle negative 45 degrees. So it will be negative 45 degrees and this value is 5√2. So I can show you another approach for drawing impedance diagram. So the method is, if you start with R, so your R is this, then you go for XL, ZL, so the inductive reactance, that is J5, and from the top of this you go for directly opposite to J10. So now from the beginning, a starting point to the end point shows you the resultant. So just first draw the vector, one vector R, then from the head of this one vector you draw XL, and from the end of this XL you draw the XC. And this is your final point, and this is the starting point. Join this start to the final point, you will get the resultant. This is called impedance diagram. So this is your total impedance, ZT, total impedance. And if I wanted to draw the phasor diagram for this, how to draw? So you got voltage equal to 50/45, current equal to 5√2 angle 90. So you have to write, so this is, let's say this is your reference line, and then voltage makes 45 degree. So draw voltage makes 45 degree and current makes 90 degree. Current makes 90 degree. So this is your phasor diagram, and from this phasor diagram you can see current leading. As it is obvious here, you see we got resistance, so current will be in phase. For inductor, current will be lagging. For capacitor, current will be leading, but this capacitor has a stronger reactance in comparing to the inductor. So the capacitor is dominating, that's why you are getting leading current. Now consider an RLC parallel circuit. So in this parallel circuit we are given R equal to this, L equal to this, C equal to this, and this is the voltage excitation. So now I convert this voltage to frequency domain. This will be 50 angle 60 degrees, and this will be 5 J0, or you can write 50 degrees or simply 5. And here L is JXL or J omega L, and omega is 500. You can see here 500, and this is the L value, so equal 2.5. In rectangular form it will be J 2.5, in polar it will be 2.5 angle 90 degrees. So J is equivalent to angle 90, and the C, Z3, is negative JXC or negative J 1 over omega C. Omega is 500, C is this, so you'll get 2. So 2 90 degrees or negative Z2. Now if you want to find the total impedance, so you see these three impedances in parallel, so the total impedance will be 1 over Z, 1 over Z1, 1 over Z2, 1 over Z3. So just this. Yeah. So now if we want to find the current for the to the resistor, yeah. So now if you want to find current, so this is will be the voltage divided by the impedance here. So voltage over Z1 is the current, and similarly current in this inductor is voltage over the impedance of the inductor. So get this, and for current in this branch will be voltage over the reactance of the inductor capacitor. Get the current. Now I1, I2 over I3 in the three currents. So the total current will be I1 plus I2 plus I3. So you got total current, or you can find the total current equal to V over the total impedance. The total impedance we calculate was this. So the total current is this, and we can verify this work by adding I1, I2 plus I3. So if you add I1, I2, I3, you will get I1, I2, I3 11.63 or 11.18, right? That was 11.182. So therefore the KCL in frequency domain holds, right? And for KCL, because if KCL says in any node the incoming current is equal to outgoing current. So here if you see the current incoming current is I1 and outgoing current is I2, I3, I1, I2 and I3. So that according to the KCL, if we apply KCL in this node, then this entering current is equal to the sum of the leaving currents, and we can also prove that the sum of these leaving currents is this, and the entering current and also the total current is the same, is 11.618 and also 11.18. So KCL holds. Similarly, we can prove that Kirchhoff's voltage law also holds in frequency domain. And here this is the diagram for Phasor diagram. So in this diagram you can find the total current I and voltage. So voltage got the expression 50 angle 60 degrees. So this is your voltage 50 60 degrees, and the current is 11 on 886. Current is 11 on 886. 11 on 8 and it is 86. So this is the relation between voltage and current, and here says you see current is leading. Current got higher angle, so current is leading the voltage. And if you want to show the total current, I1 is the current for resistor, I2 is the current for